Hey, it's Neil Smith here. Hope you're doing well. The following problem seems a bit overwhelming, but be patient with yourself. It's just adding, subtracting, looking some numbers up in tables, throw in a few nuances, a couple concepts to keep straight, and before you know it, you'll be doing these problems. They're not that bad. You got this. Determination of compass error by azimuth of the sun. Practice problem 10. We are on problem 10. Last problem in the set. And we have our givens. Our givens are the date. The first thing they give us is the date, June 27th. Date. June 27th. And the vessel's zone time is 8:16. Zone time equals 8:16, and then we're given the DR position. DR position is equal to latitude 2214 south, lat 22 degrees 14 minutes south, longitude is equal to 53 degrees 52 minutes west, 53 degrees 52 minutes west. When the azimuth of the sun is observed, so we need azimuth of the sun, which is the bearing of the sun bearing, and they say it's sun is bearing 47.5047.5 degrees PSC per standard compass. And up here they give the chronometer time of the site is 12:15:02. It's the chron time. Chron time is equal to 12:15:02, 12 hours, 15 minutes, 02 seconds, and the chronometer error is 0.46. So the chron error is equal to 0 minutes, 46 seconds, and it gives us another detail here, slow. If the chron error is slow, we add it to catch up. Variation 6 east. Variation is equal to 6 degrees east. And then it asks us a question. What is the deviation of the standard magnetic compass? So deviation, what is deviation? First thing we're going to do, we need to get the approximate GMT. Where are we? I like to call it the approximate GMT. So we know essentially if we're what side of the planet we're on. Is it day or night? So we take the zone time, which is equal to 8:16, 0816, and we need to figure out how far away we are from Greenwich Mean Time, or the prime meridian. So you can take your longitude, which is 53 degrees 52 minutes west, divide the degrees by 15. I kept the 52 because that's almost another minute, but let's check this out. 53 divided by 15, 53 divided by 15 equals 3.5. So it equals 3.5. This 0.5, this rounds up. We need to get to a whole hour. So we're 4 hours, right? And now we need to figure out, do we add this or subtract it to the zone time? Well, we're in the west longitude, so let's draw up a little diagram here to help explain it. Our diagram, this is the prime meridian, 0, 0, 0. This is Greenwich Mean Time. The time zones, let's draw in some time zones. If you go to the east, you add. If you go to the west, you subtract. If you're in New York, and you go west, you're going to subtract 3 hours to get to California time. Cool. And now we know it's west, so we're over here, so we need to come back to the prime meridian. We need to add to get back to Greenwich. So we're going to add this 4 hours. So add 0, 4, 0, 0. So that's 16 and 12. 12, 16. This is our approximate GMT. And it's in the same day. This exercise shows you what day you're in too, because sometimes these degrees can be so high that you're like adding or subtracting 10, 11 hours. So this is June 27th. And all of them take place 1981, all these Coast Guard questions. So let's find the actual GMT. The actual GMT, we'll use the cron time. So the cron time is equal to 12:15:02. 12:15:02, and that's hours, minutes, seconds. And then we'll apply the error. And the error, we have to know whether we add or subtract. So the error is 0 minutes, 46 seconds, slow, we add. So we're adding 0 minutes and 46 seconds. Let's add that up. 46 plus 2 is 48 seconds, 15 minutes, and 12 hours. Okay, so you can see here, 12:15, 12:16. We're in the right day. We're in a chronometer is based on 12 hours, so you have to figure out if it's day or night. So here's the actual GMT. So the GMT is equal to 12 hours, 15 minutes, 48 seconds on June 27th. And with this GMT, we can find the GHA, or the Greenwich hour angle, GHA. And we do it in two parts. We do it first with the 12 hours, and then we'll find the GHA of the increments, which are 15 minutes, 48 seconds, 15 minutes, 48 seconds. So we'll get what those equal. And at the same time, we're going to find the declination, because the declination is right across from this GHA for 12. And then there's also a D value that we're going to get out of there as well. So we'll set that up. And now we'll go into the Nautical Almanac for 12 hours. So first, June 27th. So December, September, July, it's going to be the next June. There it was, June 27th. June 27th, GMT. Here's the day, 27. The hour, 12. There it is. 359, 15.8. 359, 15.8. 359, 15.8 degrees minutes. And the declination is right across from that, 359, 15.8. Declination, see it here? Declination, degrees minutes, is 23. North, 2319.0. North, 2319.0. North, 2319.0 minutes, degrees. Let's get our D correction now. That's if you come down all the way to the bottom, here on the bottom, that D correction. See it? D, 0.1, okay? 0.1. Now, do we add it or subtract it is our question. The way we find that, we come to June 27th for 12 hours. Here's the declination we got. Slide down to the next hour. Is it bigger or smaller? Smaller. It's declining as we go down. So we subtract this tiny D correction. Okay. Now we need to get increments and corrections table. So we come back to the increments, and we were looking for 15 minutes in our increments. It's at the end of the book, 55. 11, 15. So here they are, 15 minutes up here in the top right, and then it's in this column. So here's the 15 minutes, and then it goes into seconds. See that little S? So seconds. We're at 15 minutes, 48 seconds. 15 minutes down to 48. 3 degrees, 57.0. 3 degrees, 57.0. 3 degrees, 57.0 minutes. And now, that's the increments part, and now the corrections. This 0.1 D value has a correction. Yeah, that 0.1 has a correction, and it's in here. Here we are. Here's the 0.1. It's 0.0. It's nothing. But if it were something, we know that we're subtracting. It's nothing, and we will add this up. So now our declination is equal to north 23 degrees, 19.0 minutes. That's our declination. And we can get this, we add these up, we'll get GHA, the sun. So 15.8 and 57. 15.8 plus 57 equals 72.8. 72.8 minutes. 359 plus 3 is 362. 362 degrees, right? Yep. Good. So this is our GHA of the sun. GHA sun is equal to this. In order, we need the LHA, the local hour angle. So we have to take our longitude, which is up here, 5352 west, and because it's west, we subtract it. So 35352. 53 degrees, 52.0 minutes. Okay, so let's do this subtraction. 72.8. 72.8 minus 52.0 equals 20.8. 20.8 minutes. And then 362 minus 53. 362 minus 53 equals 309. 309 degrees. So our local hour angle, LHA, of the sun is equal to 309 degrees, 20.8 minutes. Now that we have this information, we can put these into a table and do some calculations. So it starts out, we need our declination. We need our DR latitude, DR lat, and we need our LHA that we calculated. Good. And so what's our deck? Okay, here we are. North 23 degrees, 19.0. North 23 degrees, 19.0 minutes. And then our DR lat is 2214, 22 degrees, 14 minutes south. North and south, take note of that. And then LHA, 309, 20.8. 309 degrees, 20.8 minutes. Now we can get some information that we need just from these. So our declination and DR latitude have opposite names. This one is south, this one is north. So we can say our declination and DR lat are contrary. You'll see when we get into the tables, that's important. They're contrary to each other, north and south. If they were south and south or north and north, they'd be the same. But in this case, they're opposite, so they're contrary. So with this, we get our base argument now. And the base argument is just simply the degrees. 23 degrees, 22 degrees, and 309 degrees. And with those values, we can get our base angle or base Z. And we get our base Z from the site reduction tables. Done with the Nautical Almanac. Site reduction tables. We take those values, see these LHAs? So LHA is here on the top, and one page is contrary, and the other page is the same. And then you have, these are the DR lats, 23, 24, 25, 26, but it doesn't cover many, right? And you'll look, our DR latitude is 22. It's not even on here, but there's 2 halves to this page, or to this book. So I need to find 309 on the other side of this book. Watch these numbers right here. Watch this, 309. If you keep flipping, it'll go up and up and up, and then watch, it'll bounce back. Now it's in the 200s. It was just at 3, and it's going up. So now we need to go up to 309. 309. But now look at the DR lats, 15, 16, 17, 18. It's the lower ones. So we're contrary, 309, and then the declination is 23, which this is the declination column. 23. So contrary, 309, 23 declination, 22 DR lat. In the Z column, 129. 129. That's our base argument. 129, and it travels all the way down here. Now we need to get our tabulated Z. This one is weird. Because how you do this, you take 23, raise it up by 1. So you're 24, 22, 309. And then you record it here, and you come down to this, and so it's 23, 23, 309. Record it here, and then you get 23, 22, 310, and record it here. So let's do that. So the first thing we do is take our declination up by 1. So we're looking for 24, 22, 309. So here we are. We can just, this is the easiest one to find. So you just slide your deck down by 1. And now we're 309, we're contrary, we're 22, 24. 129.8. 129.8. And now we bump. So this problem's kind of funny. If we bump 22 up to 23, let's try to do that. Watch what happens. Come over here. Our last DR lat is 22. So we have to flip all the way back in the book, and we will. But let's get our LHA. Let's do the calculation for LHA first. So this bumps to 310. So we're 23, 22, 310. And yeah, here we are. So contrary, 310, 22, 23. 129.6. 129.6. Now we need to bump this one up. So we need to do 23, 23, 309. But to do this one, watch. We got to flip all the way back here. So we can't do it, right? We got to find 310 on this side. 310. Here's the 23. So now we're contrary. 310, 23. No, 309. There. Contrary, 309, 23, and deck of 23. Okay, contrary, 309, 23, 23, 129.3. Good. 129.3. 129.3. Excellent. Now we need to find the difference The difference in the angle between the base and the tabulated, or I should say the tabulated and the base. So do tab minus base to make sure you get the right sign on your number, whether you're adding or subtracting it. So these are actually all pretty easy because see how they're all 129, 129. And so these are all more by their decimals. So 0.8, see 0.3, 0.6. How I did that. And now we need to get the increments. So the increments are simply these minutes. The increments here are 19.0, 14, and 20.8. Those are the increments. And now we can find the correction. So the correction is equal to the difference times the increments divided by 60. So the difference times the increments divided by 60. That's our correction. So let's just punch that in. So we're looking at 0.8 times 19 divided by 60. 0.8 times 19 equals divided by 60 equals 0.25. 0.25. And now we're 0.3 times 14 divided by 60. 0.3 times 14 divided by 60 equals 0.07. 0.07. And now we're 0.6 times 20.8 equals divided by 60 equals 0.21. 0.6 times 20.8 equals divided by 60. 0.21. Okay, we add these things up to get our total correction. Total correction equals 0.25 plus 0.07 plus 0.21 equals 0.53. 0.53. That we're just going to round that down to 0.5. And now we take this total correction and add it to the base. So our base correction, our base Z rather, base Z is equal to 129. And our correction for the angle is equal to positive 0.5. So our Z value comes out as 129.5. 129.5. But this is named in quadrantal notation. So first we need to, is it north or south? We name it with the DR lat. That's south. So we put an S here for south. And now, is it east or west? The LHA tells us this. If LHA is greater than 180, is equal to east. If LHA were less than 180, it would be equal to west. So we're east. So now we're south 129.5 east. Now we need to find ZN, which is the angle from north. This is the angle from south towards the east. We need to find the angle from the north. What does that equal? You can find it in the site reduction tables. It says at the top of each page, it gives these, but I like to map it out. So let's just draw a little graph here. Let's draw it right on the line. Okay. Okay, so this is north, south, east, and west. So we're south, right? This is where we are. From south, we're 129 degrees towards the east. So we're like past 90. We're up here, somewhere up here. This is our Z value. Well, the problem is like we need Zn from the north to here. This is our Zn. So what do we need to do? We need to take this full 180 and subtract the Z, and that'll give us Zn. So we're going to say that Zn is equal to 180 minus Z. Let's do that up here. Zn is equal to 180 minus Z, which is 129.5. So our Zn is equal to this 180 minus 129.5 equals 50.5. Zn is equal to 50.5 degrees. And so let's correct our compass. We can say TVMDC, true variation magnetic deviation compass. True is we just calculated it, 50.5 degrees true. Variation was given. Variation equals 6 degrees east. 6.0 degrees east. What do we do with the east? Well, I always draw this. When we're going down from true to compass, we add west, which means we do the opposite. We'll minus east. And if we're going up, we do the opposite. So we subtract east in this case. 50.5. 50.5 minus 6 equals 44.5. 44.5. And now our compass was given here. It was sun bearing 47.5 PSC. So it was 47.5 degrees PSC. And now to go from 44 down to 47, we need to be adding to get from 44, so it's west. So 44.5 minus 47.5 equals 3. So we're 3.0 west deviation. And this is the answer we're looking for. So if we come into the problem and start looking at the answers, there we are, C. So the answer to determination of compass error by azimuth of the sun, practice problem 10, is C, 3 degrees west.